right? Over the next slide, it says the DC quiescent point power. Sorry. So DC quiescent power is defined as the power dissipation of transistor when no signal input is when no there is no signal input. So it will be the product of its Q current and voltage, Q point current and voltage. So remember that what it says, that whenever you have amplifier, right, and it has just a DC biasing, okay, it has a DC biasing like R1 and then R2, remember, okay, and then it is connected to VCC, okay, VCC, okay. So in this case we don't have any V in, no sinusoidal or input signal, okay, we don't have any V in. So basically it will be the product of so the DC quiescent power would be, by definition, would be voltage into times, okay. The quiescent point, at the quiescent point I can put this IC is equal to ICQ, and from the DC load line, okay, I can say that this VCC is equal to 2 times VCEQ. So basically this is equal sign, remember, okay. So I put the value, IC becomes ICQ, this one, okay, and VCC becomes what, 2 times VCQ. So I will put 2 into VCQ, okay, at the quiescent point. So this is how we can calculate quiescent point power when there is no input signal, right? Sometime we need this, okay. This is a quantity. And then the output power, how it is defined: the output power is the output signal power, the product of RMS load current and RMS voltage, right, okay. And this, the maximum unclipped IC signal occurs when the Q point is centered on the AC load line, right. So it means that whenever, what happens that if you have if I say for any like for this amplifier, okay, I can grab them again, I can see over here, okay. If I connect this to a load, okay, which is RL, okay, this is RL, okay, and this is some RS, I can say this one is RS, and this is V in, I can say they can be in, right, okay. Now the output power delivered to this, okay, P out maximum, okay. So this is another characteristic. So we can, by definition, if I can see this is P out at the output of the amplifier, okay, okay. So I can say this is again VC times IC, okay, okay, by definition, okay. Then since this is over here, the signal is given, the AC signal, so basically this output power is the output AC power. So it means that what would I do, this is AC voltage value, this is AC current value, okay. So I can put this as RMS value, I can equate this as 0.707 times IC, and this is, I convert this again to 0.70 times 7 VC. It means that there will be no RMS values. Remember, this output power is your AC power, this power is your DC power, okay. You put the values, so at the Q point, okay, I can call it ICQ and VCQ, okay. And this, if you okay, what happens that 0.707 times 0.707, it will become like 0.49 something. So I believe it comes, the 0.5 comes from the product of these two RMS quantities, right, okay. Now this is an example. The example says 7.1, it says they determine the voltage gain and the power gain of a class A amplifier in the figure. Assume beta AC is equal to 200 for all transistors. So remember, this is a class A amplifier, okay. So we can see this is a common emitter amplifier, okay, and this acts as a load to uh, the common emitter amplifier, because this is connected, okay, from the collector of the common emitter amplifier, and this is a load as well. So this is Darlington pair, remember, this is Darlington pair, okay. And because we have Q1 and Q2 and Q3, the base of the Q3 is fed from the emitter of Q2. So this is Darlington pair, okay. Now, and this is the load which has 8 ohms, okay. So the amplifier, the driving amplifier is this amplifier. The driving amplifier is your Q1. So I'll take this as my reference, okay, Q1 amplifier. So what happens that over here, let's suppose I start with power gain. So power gain by definition, okay, it is AV square, last time we derived it, R in total divided by RL, okay. What is the value of RL? RL is 8 ohms over here, okay, this is 8 ohms. What is the value of R in total? Okay, R in total is basically the input resistance of this class A amplifier, remember this, okay. So by definition, okay, the input resistance of this class A amplifier would be R1 parallel to R2. R1 is over here, parallel to R2, and parallel to beta AC, okay, and RE1 plus RE prime, okay. Now remember, we are dealing with this, okay, over here, from here to here, okay, with this amplifier. So we can see over here in this amplifier, if I remove the mode over here, so basically okay, so from here to here I'm interested, okay. R in base, remember we worked out this R in base for, or the R in total for this amplifier, which is a common emitter amplifier. So remember, we would have like this will go to short if this R in total I find at the AC, okay. So this would be like R1 into R2 parallel, okay, and then I have what I have R in base, R in base, R in base, okay. And this is basically what, this is your R1 and this is your R2, okay. So the equivalent resistance is given by this formula, if you see over here, okay. This is R1 parallel R2, and R in base would be, okay, it would be remember beta AC times RE prime, but because of the sweeping resistor, remember, so the AC resistor, the AC signal would find a way from RE, and then it will go this path through the capacitor C2, so this will get bypassed, okay. So effective resistance, AC resistance, would be the addition of RE1 plus RE small re prime, which is this one, okay. And beta is given, which is 200, R1 is given 56, R2 is given as 10, okay. So the only thing we need, and RE is also given as 68 ohms. The only thing we need is to find RE prime, the small RE prime. So how can I find the small RE prime? The small RE prime I can find over here from this over here, remember, okay. By definition, that this RE prime is equal to 25 millivolts, okay, millivolts divided by IE, okay. Remember, we have IE, okay. So basically, how can I find IE? So IE, I can find it from VE, so that will be equal to I can find VB, okay, which is equal to actually what, VBE and plus VE, okay. VBE is 0.7, VB is equal to VCC times R2 into R1 divided by this, and RE is fine, so I can easily find now RE, okay.